Hi guys, if you are watching this video in order to learn the merge operation in leftist trees, or if you are watching this video in order to learn merge operation in leftist heaps, you are at the right place. Because in the previous video itself I explained that there is no difference between a leftist tree and a leftist heap except this property. So in case of a leftist tree, it is actually a binary tree, and for all nodes in a leftist tree, the S value of the left child of all nodes is greater than or equal to the S value of the right child's, right? So when any binary tree which follows these two properties, that is known as a leftist tree. So in addition to that, if something follows these two properties and it also follows the heap ordering property, which says that all nodes are greater than all its descendants in case of max heap. So now in the previous video, apart from this, we also learned how to calculate the S value or the rank of any node in a binary tree. And we also saw what is a leftist tree, the properties of leftist tree, and then what is a leftist heap. But the most important thing that we derived in the last video was that if we want to merge two heaps, it will take us order of n log n time. So the time complexity of merging two heaps is very high if those heaps are binary heaps, if their representation is in the form of a binary heap. So we learn the merge operation in leftist heaps because instead of representing the two heaps as binary heaps, we will represent them as leftist heaps and then we will merge them. That will take a lesser time complexity, right? So now what I am going to cover in this video. So in this video, I am going to show you an example where I merge two leftist heaps. So first we will look at the examples and then we will derive the steps out of the examples, right? Then we will write down the code for merging two leftist heaps, and then finally we will try to find out the time complexity of this operation of merging two leftist heaps, right? And in this video, we will refer to min heaps. So in min heaps, the value of a particular node is less than all its descendants. As in this case, you can see the value of 1 is less than all its descendants. The value of 8 is less than all its descendant nodes, right? So we are looking at min heaps, but we can also apply the same steps for max heap. So we will learn all this in case of merge operation between two leftist heaps. And in the next video, we will learn how to insert a new element in a leftist heap and how to delete an element from a leftist heap. The reason why I am teaching you the merge operation first is that because in the next video, we will learn that in case of a single insert operation, a sub operation is actually a merge operation. Even in case of a delete operation, we will also perform merge operation when we do delete an element from a leftist heap. That is why it is required that we know how to do the merge operation first, and then in the next video we can learn the insert and delete operation as well as how to initialize a leftist heap. In this video we will be looking at merging of two leftist heaps, but the steps are same but the steps are exactly same when we want to merge two leftist trees as well, right? So in this case, I have taken two leftist heaps. We want to merge these two leftist heaps, right? Let us name these leftist heaps as A and B. So what we do is that we look at the root of A and the root of B and we find out that which leftist heap has a smaller root, okay? So in this case, the root of A is 1, the root of B is 3. So A has a smaller root. Then what we do is that we apply the merge operation again. In the first case, we have applied the merge operation between these two leftist heaps, right? This is the first case. So in the first merge operation, we apply the merge operation between these two leftist heaps, right? So this is the first merge operation. So in the second step, what we do is that we look at both the leftist heaps and we see that which leftist heap has a smaller root, okay? So the root of A is 1 and the root of B is 3. Okay, so A has a smaller root. Then what we do is that we take the left subtree of A and we apply the merge operation between the left subtree of A because it has a smaller root and B, right? And the complete B. Okay, right? So let me write down that the merge operation will be applied between which two leftist heaps in the second merge operation. So the second merge operation will be applied between these two leftist heaps, right? So in the next case, we will apply the merge operation between the right subtree of A and the complete B, right? So this was the right subtree of the previous A and this is the complete B. So now this will be our A and this will be our B, and this is our second merge operation, right? This is our second merge operation. This was our first merge operation. Again, we will do the same step. We will compare the root of both the leftist heaps and we will see the smaller root. Okay, so the B has the smaller root 3 while A has root 8. So as 3 is less than 8, so we will take the right subtree of this leftist heap, right? We will take the right subtree of this leftist heap. Here we took the right subtree of this leftist heap because its root was less than the root of this leftist heap, but here we are taking the right subtree of this leftist heap when we merge these two leftist heaps, right? So basically, if you understand that the merge operation is recursively applied over here at the right subtree of the previous A and B, right? So then again we will apply the merge operation between the right subtree of this leftist heap because it has a smaller root and this complete leftist heap, that is 8, 11, 16. So let me write down that the third merge operation will be applied between which two heaps. So now in the third case the merge operation will be applied between these two leftist heaps, right? Here we took the right subtree of this leftist heap because it had a smaller root and we applied the merge operation with this complete leftist heap. So 8, 11, 16 we have taken as it is, right? This becomes our A and this becomes our B. But this B is actually the right subtree of the leftist heap that had the smaller root. Okay, so here we will apply the third merge operation. Now again let us look at the root of both the leftist heaps. Which has a smaller root? This B has a smaller root 7, right? So let us apply the merge operation now between the right subtree of this leftist heap which has a smaller root and this entire leftist heap. So this complete leftist heap we can write it down as it is. And what is the right subtree of this leftist heap? It is null, right? It is null. So we apply the merge operation over here. So this is our fourth merge operation. Okay. So this was our first, second, third and fourth merge operation. So every time what we are doing? We are actually comparing the roots of both the leftist heaps. Here we compared the root of 1 and 3. We saw that 1 is smaller. So we take that leftist heap. So we make a new leftist heap out of the leftist heap that has a smaller root by considering only its right subtree. So we considered only its right subtree and we take the other leftist heap as it is, right? But in this case, we compared the roots 8 and 3. 3 had this B had a smaller root. So we considered its right leftist heap and we merged it with the A leftist heap as it is. So A leftist heap was as it is and we merged it with the right subtree of this leftist heap which had a smaller root. So when we compared these two, we will consider the right subtree of this leftist heap because it has a smaller root 7, but the right subtree of this leftist heap is null. So in this case, when you reach a null condition, you have to return back. So if you observe clearly, this is kind of a recursive approach that we are applying. First, in the first case, there was a recursive merge call between the two original leftist heaps. Then the second recursive call was on the right subtree of the leftist heap with a smaller root and one of the original leftist heaps, right? One of the original leftist heaps and the right subtree of the one with the smaller root. And then again, we compare over here the root of both the leftist heaps and we do another recursive call between the right subtree of the leftist heap with a smaller root and the original leftist heap in this recursive call. This is the original leftist heap in this recursive call. So if you understand very clearly, this is we are following the same steps in every merge operation. So this is actually this is the first recursive call, second recursive call, third and fourth recursive call. So if you have learned recursion, you can understand this as the base case of recursion, where if you get any leftist heap in the merge operation as null, in that case you can return from your recursive call. Okay? But while returning from your recursive call, you have to follow another step. Now what is that step? Let us see. As I've told in my previous video as well, what is the structure of a node in a leftist heap or a leftist tree? So like all the binary heaps, you have got one data, right? You have got a data. Then you have got the left child. Then you have got a pointer to the right child. And then apart from that, what else you have got? You have got the S value, right? You also have got the S value. So how do we calculate the S value? So let me show you by calculating the S value. So every node will have a S value associated with it, right? So the S value of this is 1, S value of this is 1, S value of this is 1, 1, 1, and the S value of this is 2. For calculating the S value of any node, like for calculating the S value of this root, what we do is that we find the minimum of the S value of its left child and its right child. So the minimum of the S value of its left child and right child is minimum of 1, 1, right? We are finding out for S of 1 or the S of root. Plus we add 1 to it. So this becomes 1 plus 1 is equal to 2. So I've already clearly explained how to find out the S value in the previous video. So what we do is that we return this leftist heap. This 8, 11, 16 was the final leftist heap that we got in our last recursive call. We return it, okay? And what we do is that we attach it with that leftist heap in the previous call, which had a smaller root, right? So out of these two leftist heaps, which one had the smaller root? This one, whose right subtree we transferred to the next recursive call, right? Or we made it the new leftist heap, although it was null. So we attach this new leftist heap to the leftist heap in the previous recursive call with a smaller root. So 8 is small or 7 is small. So this leftist heap has a smaller root. So we will attach this 8, 11, 16. We will attach this 8, 11, 16 to this 7, 10, 15. In the previous, this leftist heap was in the previous recursive call, and this was the leftist heap that we are getting as a result of our last recursive call, right? So we are going backwards now. We are going backwards. Fine. So now pay attention. We just directly cannot attach it as the right child of this leftist heap in the previous call. In order to attach this leftist heap to this leftist heap, we actually have to follow this property of a leftist heap, that for all nodes, the S value of the left child of that node is greater than or equal to the S value of the right child of that node, right? So accordingly, according to this property, we have to attach this leftist heap that we are getting from the I plus 1th recursive call to the leftist heap in the ith recursive call. And which leftist heap are we talking about over here? We are just talking about the leftist heap that had a smaller root. Now, we are not considering this leftist heap because that is something we transferred to the next recursive call. But we didn't transfer this leftist heap. So we have to attach it to the remaining part of this leftist heap. We have already transferred the right child of this leftist heap. So here this null node or the external node was transferred over here, but this part was not transferred. So to this leftist heap, this has to be attached. So for that we need to follow this property, right? For that property, we know that these nodes will have their associated S values. So this will be 1, 1, 1, and S value of this will be 1, this will be 1. So in a case when, so as you can see, if we attach this thing at the right child of 7, in that case, this property will not be violated, right? It will not be violated because the S value of 7's left child will be 1 and the S value of the 7's right child will also be 1. So it is greater than or equal to, so in this case it is equal to, so we can attach it over here. So we can attach this leftist heap that we got from the next recursive call over here, right? Why? because the S value of this is also 1 and the S value of its left child is also 1 and the S value of its right child is also 1. So when this property we see it getting violated, that we will see in later on, in that case we need to swap the left subtree and the right subtree. Okay, but now let us repeat this process. So in this recursive call, while returning, this is the leftist heap that we got, this complete leftist heap, right, which has 6 nodes. Now we are going to return this leftist heap, okay, in the previous recursive call. So now in this leftist heap in the previous recursive call, so now in the previous recursive call, we will consider that leftist heap, okay, we will consider that leftist heap which has a smaller root, right? So which one has a smaller root, this one or this one? This one has a smaller root, right? So we will take this leftist heap in order to merge with the leftist heap that we are getting from the successive recursive call, right? So this is so now we are returning, right? So we return from here to here, and now we will merge this leftist heap with this leftist heap that we didn't transfer to the next recursive call. So if you clearly notice that the root and the left subtree of B we didn't transfer to the next recursive call when we were going forward, right? We just transferred to the right subtree. As you can see, the 7, 10, 15, we just transferred the right subtree. So now we have to merge the left subtree and the root with this leftist tree that we are getting from the successive recursive call. So we are not interested in this part, right? We are not interested in this right subtree of this leftist heap because we have already transferred it. We will already get it in our result over here, right? So now we want to merge this leftist heap and this leftist heap, or you can say we want to attach this leftist heap and this leftist heap. We need to find out the S value of, so S value will already be stored with all the leftist heaps. So the S value of this is 1, this also 1, 1, and S value is 1, 1, and what is the S value of 7? It will be 2, okay? And what about the S value in the case of this leftist heap? So let me draw this leftist heap over here. So so basically this leftist heap and this leftist heap only has to be merged, right? So we have to merge this one and this one. So we need to check if it is following this property or not. So all the nodes will have an S value associated with them. Like this node has an S value of 1, 1, 1, 1. All the leaf nodes have S value associated as 1. And this will have an S value of 2. This will have an S value of 2, while this will have an S value of 1. Compare the S value of the root of the left subtree, right? This is the root of the left subtree, that is 4, and this leftist heap and the root of this leftist heap, right? So we compare their S values. So now both their S values are 2. The S value of 4 is also 2 and the S value of 7 over here is also 2. So their S value are equal. So we will not violate this property, right, of S value of left of x is greater than or equal to S value of right of x. In case of this root, when we consider this root as x, right, we will not violate this property if we attach this entire leftist heap as the right child of this leftist heap. So let us attach it as the right child, this root of this leftist heap. As you can see, I have attached this leftist heap that we were getting as a result of the successive recursive call along with this leftist heap, along with the left subtree and the root of this leftist heap that we didn't transfer to the next recursive call, and I have attached it as the right child. Why? Because even if I attached it as the right child, the S value of its root will be 2, and even here the S value of the left subtree of this leftist heap is 2, so it doesn't violate this property that the S value of the left child is greater than or equal to the S value of right child. So I can very easily apply it over here. Moreover, you will also find that it is also following the heap ordering property, that the value of any node is less than all its descendants. As you can see here, 3 is the minimum node, is the minimum value node in this entire leftist heap. So all the properties it is following, it is still a leftist heap. But we are still not returned to our first recursive call, right? So this was our first recursive call. So this is the result that we will get in our second, so this is the result that will be returned from our second recursive call, okay? So now, pay attention. So now we need to merge which two leftist heaps? This leftist heap that we are getting as a result and the left subtree and the root of this leftist heap that had a smaller root. Because if you'll notice, this part 1, 10 and 12 were not transferred to the next recursive call. So we will merge this and this, right? So let us draw both of them. So we have to merge this and this, right? So if you see, the S value of 10 is 1, S value of 12 is also 1, right? And S value of 1 is also 1, because everywhere over here we are having external nodes, right? So now this leftist heap that we will be returning, what is the S value of its root? Just check the S value of the root of this leftist heap. The S value of the root of this leftist heap will be minimum of the S value of its left child and right child. So minimum is 2, 2, minimum of 2, 2 is 2 plus 1. So the S value of the root of this leftist heap will be 3, right? So now again we need to check, if we attach this leftist heap with the root 3 as the right child, okay, will it violate the property that the S value of left child is greater than or equal to the S value of right child for all the nodes? Yes, it will violate. Because if we attach it over here, as you can see, the S value of 3 is 3, okay, and the S value of 10 is 1, right? If you consider this root as x, the S value of its left child will be 1 and the S value of its right child will be 3 if we attach this entire leftist heap over here, right? So that will violate this property. That will violate this property, that S value of left child is greater than or equal to S value of right child for every node. It will violate it when we consider the root as the particular node. So the S value of its left child will be 1, that is less than the S value of its right child. So in this case, we cannot attach this leftist heap over here. So what we have to do? Rather than attaching it as the right child, we will attach it as the left child. So what will happen to this left child? This left child over here, it will be attached as the right child. So we'll basically swap. So what we considered was that we will be attaching this as the right child, but that was violating the property of leftist heap. So we will swap both the positions. The left child will become the right child and the right child will become the left child. So I'll draw the leftist heap after attaching the left and the right child. So if you see here clearly, this is our final leftist heap after merging both these two leftist heaps. This is the final leftist heap that we'll get. So in the last step, what we did was that this leftist heap, instead of attaching it as the right child of this root 1 of this leftist heap, we attached it as the left child because its S value was 3, right? And we attached this leftist and we attached this part, this 10 and 12 as the right child because it had a smaller S value, that is 1. And we also want to maintain this property that the S value of left child is greater than or equal to the S value of right child. So now let us write down the algorithm. So let us consider this function, right, of the merge operation. So this function will return the root of the merged heap, whereas these two parameters are the root of the heaps that have to be merged, right? This is the root of the heap 1 and this is the root of the leftist heap 2, right? So now what we do first is that, as this is a recursive function, it is better if we write down the base condition first. So if root 1 is equal to null, as these are pointers, so we return root 2, right? And then we write, if we can also write it this way, if root 2 is null, then we return root 1, right? This is simply the base condition. Now let us declare some pointers. I'll tell you later why we need this. So now what we have to do? Now we will compare the value of the root of both the leftist heaps that we have to merge. Let us suppose that the heap 1 has a smaller root value, right? That means the data of root 1 is small, right? So if root 1 data is small than root 2, in that case what we do? In that case, we will call a recursive call for the right subtree of the in that case we will call a recursive call for the right subtree of root 1, right? Why? Because it has a smaller root. So let us call a recursive call for the right subtree of heap 1 or leftist heap 1 and for leftist heap 2, right? So this function, so this recursive call will return a merged leftist heap that will be a merging, that where it will merge these two things, the right subtree of the first leftist heap and the second leftist heap, which we will store in another variable that is returned heap. Okay, returned heap. Okay, so now I'll also declare returned heap over here. Our final root will be root 1. Now what do I mean by this step where I do final root is root 1? So when this merge function will end, we have to return a heap, right, from this recursive call as well. So what will be the root of that heap? So the root of that heap, as you will always be the root of the remaining heap, right? The root or the root of the heap that has a smaller value, right? So that is why I have written final root is actually equal to root 1. Else the next condition will be symmetric, where rather than passing the right subtree of root 1, we will pass the right subtree of root 2. Okay. So and that recursive call will also return a merged heap between these two things, and we will store it in returned heap. And the merged heap that we will actually return from here, its root will actually be the root of heap 2. Why? Because heap 2 has a smaller value in this condition, right? And we also want to maintain the heap ordering property, right, where the finally merged heaps value is actually the lowest at the root. That property we are maintaining by calling the final root as root 2 and final root as root 1, right? So now here we are maintaining the heap ordering property, right, that the root of any heap should be smallest. It should be smaller than all its descendants. That is why we are writing final root is equal to root 1 and final root is equal to root 2. Okay, so now what is left? Now we just the returned heap that we have got over here, we don't return it as it is. Why? Because we are actually passing the right subtree of root 1, where our heap 1 has had a smaller root. So we passed its right subtree, only its right subtree. So the root itself and the left subtree is remaining. So what we finally do is that this returned heap will be joined, or it will be merged with the remaining heap, right? Returned heap will be joined with the remaining heap. So my root of the first heap, my root of the heap 1 and its left subtree is the remaining heap, and this returned heap is actually the returned heap. So I'll merge both these, right? Both of these. So now what we will do? How we will merge them? We will first check the S value of this returned heap, right? We will check that if returned heap, which is a pointer or the heap returned from the successive call, S value is greater than the final root left S value. What is the meaning of this final root's left S value? So why we are comparing it with the new root, that is the final root's left child's S value. Why we are doing that? Because we want to actually compare the S value of the left child and the returned heap, right? That is what we saw in the example. So that is why if it is greater, that means a swapping will be performed, right? In this case, a swapping will be performed. So it is initially the left child, so later we will make it the right child because we want to make this returned heap as the left child. So let us store this left child in another node, that is temp. Okay, node star temp is equal to final root left. Okay, then we will make the returned heap as the left child. So final root's left child will be returned heap, and right child will be what was originally its left child, that is what we have stored in temp, right? We stored it in temp, right? If this is not the case, then we don't need to do any swapping. We just attach the returned heap as the right child of the remaining heap, right? So we attach the returned heap as the right child of the remaining heap. Fine. Now, what else is left? Now we have finally merged the heap over here, right? So here the heap is merged. On the basis of which property? That the S of left of x be greater than or equal to S of right of x, or the right child of x, right? We have maintained this property, and then finally we will return our final root. And before that we also need to update the S value. Okay, so I'm not writing the code for that. Finally we'll return this merged leftist heap from here, right? So this was the code. Now what is the time complexity of this merge operation of leftist heaps? So if you see over here, every time what we are doing, so all these, the time complexity of everything over here is order of 1, and everything over here is also order of 1, right? This is also order of 1. So this is also order of 1, right? So the main time complexity is hidden over here. So now if you see over here, what we are doing recursive call over here on the right subtree of the leftist heap with a smaller root, right? So here also we are going to the right subtree of root 1, and here we are going to the right subtree of root 2 in the new recursive call. So how many recursive calls will be required? That will actually determine the time complexity of this algorithm. So how many of these merge calls will be required? So that will actually be equal to the rightmost path of the leftist tree, right? So suppose this is your leftist tree. So you are always going to the right side, correct? You are always going to the right subtree for any of the leftist heaps. So your time complexity will be of the order of rightmost path. We have learned that the rightmost path is actually equal to the S value of your leftist heap, right? We have learned that the rightmost path is actually equal to the S value of the leftist heap in the previous video. You can watch it in the previous video. And we have also learned in one of the properties that the S value, it is at most log to the base 2 n plus 1. So if suppose we consider that the first leftist heap has n1 nodes, so its rightmost path will be at most log to the base 2 n1 plus 1, right? And if suppose that second leftist heap has n2 nodes, so its rightmost path will be at most n2, so log to the base 2 n2 plus 1. So basically the time complexity will come out as order of log n, right? Why? Because where n is maximum of n1 and n2, right? So this will be the time complexity, because we are just traversing the rightmost path of any of the leftist heap. So this will be the time complexity. We saw over here that the leftist heap is actually giving the time complexity of the order of log n when we are merging two heaps. So if we are merging two leftist heaps, we will have the time complexity of order of log n, which is very less than what we get in case of binary heap or merging of two binary heaps, where we get the time complexity of order of n log n. And when we use heapify method, we get the time complexity order of n. So when we want to merge two heaps, it is better if those heaps are represented in the form of leftist heaps in order to get a better time complexity of the order of log n. So now as you have understood merging operation in leftist heap, it is going to be very easy for you to understand the insert and the delete operation in leftist heap, because they also contain the merge operation as a sub operation. So let us meet in the next video where we will learn the insert and the delete operation in leftist heap. That's all for this video. Thank you.